Okay. In today's lecture, I would like to talk about some fundamental things which I've observed from my experience that confuses students. And to really proceed, I would like us to look at the concept of what we shall call quantifiers. We have what we call the universal quantifiers and the existential quantifiers. Here, before I go into this, I would like us to look at the following symbols because they will play the role in what we shall be discussing in the sequel. One of the symbols is the symbol, a double arrow going this way. This symbol stands for implication. For instance, we can say a statement A implies a statement B. We can have this symbol also where we have double two-sided arrows. This is identical to imply. This one is identical to what I may say call equivalent. Or if and only if. This is also represented by abbreviated if and only if. So how is this used? We can say that a statement A is equivalent to a statement B. Or A if and only if B. So these two statements are the same. But what this means is that A implies B and B in turn implies A. So it's a double implication. The statements A and B imply each other. Then another symbol which I meet is this symbol. Even though I've used it before, but it's good we emphasize more on it. This symbol stands for given or for all or for each or for any, depending on the person using it, or for every. So any of them can be used. They are used interchangeably. So I can talk about, when I say given, it means for any, or for all, or for each, or for every. So if I write for all x in A, this means this is equivalent to for every x in the set A, and which is equivalent to for all x in the set A, which is still equivalent to given x in A, given x in A. So that's what that symbol stands for. Then another symbol is the symbol that's the mirror image of capital E. And this symbol stands for there exists, or there is at least one. Yes, there is at least one something. I think it's okay that way. We can, by the time I start putting it in use, you'll see what I'm driving at. It also means for some. It also means we can find. So these are the different clauses we can use to qualify or that are equivalent to the symbol I put down, which is a kind of a mirror image of capital E. Example, there exists x in R means we can find x in R, or there exists x in R, or there exists at least one x in R, or for some x in R. All these statements mean the same thing. So by the time we start making use of these symbols in what we shall discuss in due course, the essence of this discussion is that so that people will be carried along. And at times we mix them up. We do not know which one is which, and which one implies the other, which one can be combined with the other, or the arrangement. The arrangement of these two symbols in any mathematical statement matters. So one has to be very careful how we handle them in making certain mathematical statements. Now, the symbol of this, which stands for all, is what we refer to as the Universal Quantifier. The symbol for all is the Universal Quantifier. Why the symbol there exists is the Existential Quantifier. Example. The example I want to give now shows how these two can come together in a mathematical statement. Look at the statement. For any x in the interval -1, 1, there exists y in the same interval -1, 1 such that y is greater than x. This is a mathematical statement. This is saying that given x in -1, 1, we can find a y in -1, 1 that is bigger than x. And this is a true statement. What this means in actual sense, so that people will understand this, especially students at this the level, our target will understand it. This is saying that whenever x is given in this interval, we can find y in the same interval, so that that y is bigger than x. From now going on, let me put it here, such that will be abbreviated s dot t. This is what I will be using as such that. So let me circle it here. So we shall see s dot t as such that whenever I want to write it. So what this statement is telling us is, let me put it literally, that this statement says that whenever x is given in the interval minus 1, 1, in the interval minus 1, 1, we can find y in the same interval minus 1, 1, such that y is bigger than x. We have to be very careful here. Observe that in this statement, I started with for all x in minus 1, 1. And then continued with there exists y in minus 1, 1, so that y is greater than x. If I now write the statement, let me call here maybe I. If I write another statement I, and the statement reads thus: there exists x in minus 1, 1, such that for any y in minus 1, 1, y is greater than x. These two statements, I and I, are not the same. The two statements, I and I, are not the same. In the first statement, for all comes first before there exists. In the second statement, there exists comes first before for all. These two statements, if properly interpreted, will give us totally different things, meaning that interchanging these symbols in mathematical statement, one has to be very, very careful. Remember, in interpreting the first one, we had that whenever x is given in the interval minus 1, 1, we can find y in the same interval minus 1, 1, so that we can find y in the same interval so that y is bigger than x. Now let us try to interpret this one. Let me repeat the two statements. The first one says, the one I'm calling I, says for any x we pick in minus 1, 1, there exists y in minus 1, 1, such that y is greater than x. Remember, minus 1, 1 is the open bounded interval from minus 1 to 1. Remember our definition of open bounded interval. If we take this as the real line, and you have minus 1 here and 1 somewhere here. So we are talking about the collection of points between minus 1 and 1. Minus 1 and 1, not inclusive. Not inclusive. I'm just trying doing all these things just for clarity sake. So for any x, remember that it says whenever I'm repeating it. Whenever x is given in minus 1, 1, we can find y in minus 1, 1 so that y is bigger than x. This is the interpretation of this, meaning that given x in minus 1, 1, there exists y in minus 1, 1 so that y is bigger than x. The other statement I wrote, which I say is not the same with this, is the statement there exists x in minus 1, 1 so that for all y in minus 1, 1, y is bigger than x. This one reads that we can find x in minus 1, 1 such that whenever y is given in minus 1, 1, that given y must be greater than x. Of course, if you look at the way this reads, it's obvious that the second statement is not true. Is not true. That statement is not true. What is it saying? That I can find yx here so that for any y I pick here, that y will be bigger than x. That statement sounds somehow. And it's not true. Because what this is just to tell you the difference between the first statement and the second statement. And for you to see that these two statements, the two quantifiers, that is the universal quantifier and the existential quantifier, we must be very careful how we use them. How we use them in the mathematical statement. Interchanging their positions in mathematical statement will turn the entire statement into something else. Why the first statement is a true statement, the second one is not a true statement. And as we proceed further in this discourse, we will see the reason why I'm pointing out all these things. This is very important. What I'll point out now is very, very important and should be bear in mind. And should be borne in mind. This is very important. Very important statement concerning the universal quantifier and the existential quantifier. And it's good we mention it now. We should know that, note, whenever for all comes before there exists in a mathematical statement, whatever follows there exists depends on what follows for all. I don't know. The way this sounds, it may not be all that clear until I give an example. Let us look at the following example. In the statement for any x in minus 1, 1, there exists y in minus 1, 1, so that y is bigger than x. In this statement, we observe that for all comes before there exists. And what follows for all is x in minus 1, 1. While what follows there exists is y in minus 1, 1. So what this statement is telling us is that, whenever this for all, in any statement where for all comes before there exists, this thing that follows for all must depend on what follows. This thing that follows there exists, must depend on what follows for all. Meaning that this particular statement, as written before, is not completely proper. So to put it in a proper perspective, the right thing to write is the following. For any x in minus 1, 1, there exists y. If I put sub x, this signifies y depending on x. Or I can write y of x in the interval minus 1, 1, such that y sub x is greater than x. This signifies the dependence of y on x. And why this is so is that for me to be able to find y, x must be first given. So if you give me x, I can find y. So the possibility of getting y depends on the value of x that is given. That is why this is necessary. And as we proceed, we must always observe this and must write complete statements so that we do not put ourselves in trouble. This dependence on x means a lot. Now, the next thing we should note is the following. We note again, whenever there exists comes before for all in a mathematical statement, whatever follows for all. Example, in the statement, there exists k greater than 0, such that for any x in the interval minus 1, 1, absolute value of x is less or equal to k. In this statement, we observe that there exists comes before for all, and what follows for all is x in minus 1, 1, while what follows there exists is k bigger than 0. What we are saying is that here, this there exists, this thing that follows for all, does not depend on this particular k that follows there exists. What this statement is saying is that we can find a positive number k, so that whenever we are given a point x in minus 1, 1, the absolute value of that x will be less than or equal to k. This statement is a true statement. This k is on its own and is controlling every x in this interval, in the sense that absolute value of x is less than or equal to k. And this therefore means that X does not depend on K. This statement is different from the statement for all K greater than 0. There exists X in the interval -1, 1 such that absolute value of X is less than or equal to K. These two statements are not the same. And in fact, in the second statement, for the fact that for all comes before there exists. As we said earlier, what follows for there exists must depend on what follows for all. Meaning that here, I must write S sub K to show that dependence on K. And meaning that here will be S sub K. But if you look at this statement, you find out that this statement is totally different from this one. These two do not depict the same thing. Still emphasizing on the fact that there exists and for all, interchanging them in a statement, interchanging them may not necessarily convey, in fact, do not necessarily convey the same message. So we have to bear this in mind. So what we've learned so far is that whenever the universal quantifier comes before the existential quantifier in a mathematical statement, what follows the existential quantifier depends on what follows the universal quantifier. And whenever the existential quantifier comes before the universal quantifier in a statement, what follows the universal quantifier does not depend on what follows the existential quantifier. So I think this is, I believe, is well noted. Now, the next notion I would like us to look at is the notion of negation. Negation of mathematical statement. These things we are looking at are, to some people, trivial, but they are messing a lot of people up. They are messing a lot of people up. And this is because we took them for granted. And taking these things granted always creates a lot of problems. And where these problems are normally observed are when people maybe did not consider this important, the importance of all these things we are mentioning, and they took it for granted, see it as trivialities, and when they now want to apply them in research, you will find out that such people will find themselves in a serious, difficult situation. At times, they put down things that are not correct, thinking that they are correct. Now, given a mathematical statement that involves the existential quantifier and the universal quantifier, it is always good to know what the negation of that statement is. By the negation, I will say in quote the opposite of that statement. And to paint a better picture of what I'm trying to present, I think it's better we use example. Let us note that negation in mathematics or in any field of study is a very important notion that should be taken seriously. Now, let us consider the following statement. For any x in R, there exists n in the set of natural numbers so that n is greater than x. Look at that statement. For any x I pick in the set of real numbers, there exists n in the set of natural numbers so that n is bigger than x. This is a mathematical statement and is a true statement because given any real number, there is a natural number that is bigger than that real number. This is a statement. Let me say statement. Its negation is the following. But before we can get its negation, let us lay emphasis on what this means literally. For any x in the set of real numbers, there exists a natural number so that n is greater than x. What this is saying is that whenever you give me a real number x, I can find a natural number n so that n is greater than x. Remember that our discussion and what we explained above, that whenever a universal quantifier is coming before existential quantifier, whatever follows existential quantifier must depend on what follows the universal quantifier. And for that reason, it's better we put this statement in the right perspective by putting n sub x here. N sub x here, meaning that n depends on x. So to negate this mathematical statement, this is saying that for any, whenever you give me x in R, we can find n in the n depending on x, so that n depending on x in n is bigger than x. What would be the negation of this? If you give me this point, I can find this point, so that this happens. Its negation naturally is that I can find a point x, say x naught, in R, so that whenever you give me n in the set of natural numbers, this particular inequality will no longer be true. Here, for all x, there exists n x, so that this is true. That is not true means there is one point here, so that for anything you pick here, this inequality will no longer hold. For that reason, the negation of that particular statement is the following. There exists a certain x naught in R, at least one x naught in R, such that for any natural number n you give me, n is less than or equal to x naught. This is the negation of this statement. Now, looking at this, to negate a mathematical statement that involves the universal and the existential quantifiers, what one should bear in mind is the following. And this rule should guide whoever is trying to do that. It's very simple rule. Replace, in trying to negate a statement, replace the universal quantifiers by the existential quantifier and the existential quantifier by the universal quantifier, and then write the negation of whatever other statement in the given statement. And that is what we did here. Observe that for all here, change to there exists, and there exists, change to for all. Then this inequality greater than is negated to what? To less or equal to. Further examples. Note that here, while the first statement is true, in the sense that given any real number, we can find a natural number bigger than it. The second one is not true, because the second one is telling us that there is a real number, so that every natural number is less than or equal to that real number. This is not a true statement. We shall say it as we discuss further. But it happens to be the negation of the first statement. Now, let me say this. Given this statement, this second one is negation. In the same way, the first statement is the negation of the second one. So why this statement is the negation of the why this second statement is the negation of this particular one? Then the negation of this particular one is the first one. So that's what I want us to understand. Let us take another example. In epsilon calculus, we shall say this later, but I just put it down here because of the involvement of the existential quantifier and the universal quantifier in quarter rightness. In epsilon calculus, a sequence xn n equals 1 to infinity is said. In fact, let me leave this for now until I bring in things that will help us. Let me look for something else and use, so that I do not create unnecessary confusion at this early stage. Within a short time, which I introduce the concept of sequence of real numbers, and we'll now define what a sequence of real numbers is, talk about the convergence of sequence of real numbers, and boundedness, and so on and so forth. So let us leave this thing until we get there. Now, let us look at this statement. There exists m greater or equal to 0 such that for any x in the set 1, 2, minus 5, 3, minus 6, absolute value of x is less than or equal to m. Given this statement, given the statement, there exists m greater or equal to 0, so that for all x here, absolute value of x is less than or equal to m. The negation of this statement, the negation of this statement is the following statement. For all m greater or equal to 0, there exists x, of course depending on m, in the interval, in the set 1, 2, minus 5, 3, minus 6. such that absolute value of Sm is greater than m. This is the negation of the statement above, following the same pattern I've explained earlier, that to negate a mathematical statement involving existential quantifier and the universal quantifier, what one needs to do is change the existential quantifier to universal quantifier, and change the universal quantifier to existential quantifier, negate any other statement, mathematical, any other statement in that particular, any other thing in that statement, and rearrange the statement in order to make meaning. That is, rearrange the structure of your English and get something better. For example, here, there exists m greater or equal to 0, so that for all x in here, absolute value of x is less than or equal to m. Its negation is this there exists will change to for all. This m greater or equal to 0 remains. So that for all this, there exists. That second, this for all here, observe that such that didn't appear again, meaning that I'm rearranging things. And look at where such that now falls. So you smoothen it that your English will flow. So there exists m greater or equal to 0, so that for all x here, absolute value of x is less than or equal to m. The negation of this statement is for all m greater or equal to 0, be observing this, that there exists has been changed to for all. Then this for all change to there exists xm greater or xm in this set, so that this happens. Observe that we are now obeying rules. Here, there exists m greater or equal to 0 comes before for all x here, and by our rule, that what follows for all does not depend on what follows there exists, because there exists comes first, comes before for all. But in this case, for all m greater or equal to 0, this for all comes before there exists. So whatever follows there exists must depend on what follows for all. And thus we have the following statement. This statement is the negation of the other statement. As we proceed, we shall be meeting other mathematical statements that require that we can talk about their negations. Maybe I'll give one more example. Let us consider the family of sets, say gamma. Consider if the family gamma of sets, say A alpha, so that alpha is in some index set, say I. If we recall our elementary set theory, we know that we can talk about union over alpha in I of A alpha. And we can also talk about the intersection over alpha in I of A alpha. This union says is nothing but considering all A alphas and putting together everything that belongs to each of them. The intersection is telling us nothing but bringing together only those values A alphas have in common. This we know. So, based on this, we can see that if we take x in the union over alpha in delta, over alpha in I of A alpha, what does this mean? This implies whenever we take X in this union, what does that mean? X in the union therefore means that X is in at least one of the A alphas. X is in at least one of the A alphas. Being in at least one of the A alphas, how do we put it? How do we represent it mathematically? So what this means is that there is a certain alpha, maybe we'll call it alpha naught, in the index set I, so that X belongs to A alpha naught. That is what it means. So this means that there exists alpha naught in I, so that X belongs to A alpha naught. So this is a true statement. Now, I want us now to look at the negation of this statement. I want us to look at the negation of this statement. Negation of this statement means, what does it mean that X is not in the union? So, from what we've learned so far, X is not, this is symbol for X is not an element of. X is not, remember this is element of. X is not in the union over alpha in I of A alpha. What does this imply? Remember that X in the union means that there is a particular alpha naught. So that there is at least one A alpha that contains X. Meaning that there is a particular alpha naught in I, so that X belongs to A alpha naught. So the negation of this statement is that's to say that X not in that particular union. What this means is that for any alpha you give me in what? In I. For any alpha you give me in I, X is not in what? In A alpha. So X not in that union means that for any alpha in this, X is not in A alpha. Meaning that none of them contains X. And therefore that X will miss being in their union, because their union is the collection of all the members of those sets. Similarly, X in the intersection alpha in I of A alpha. This implies that, look at this, X in the intersection. Remember that the intersection is what these sets have in common. Therefore, whenever we pick X in their intersection, what that implies is that for any alpha in I, X belongs to A alpha. So, X not in the intersection over alpha in I of A alpha will imply that there exists alpha naught in I such that X is not in A alpha naught. So these are some elementary facts that are taken for granted at times, and they kept on causing confusion, especially when somebody thinks that he or she has arrived to start doing mathematics. So I will urge the listeners to try as much as they can not to take things for granted. Read in between lines, study in between lines. Everything written in mathematics is very, very important. Otherwise, it wouldn't have been written. we should take our time to go to the foundation, to the scratch, and still build up from there in order to be able to be acquainted with all these mathematical rules. And with that, you'll find out that our mathematics will flow freely. What I mean by flowing freely is that there will be not much difficulty in understanding mathematical concepts once the ingredients that build the concepts are properly understood. I think this is a good place to stop this particular lecture. And it is my hope that we shall meet in a short while. Thank you so much for listening.